Yeah, so I'm going to tell you about attention today. This is joint work with Zhao Song from Adobe. Okay, so what is attention? Well, attention is a technical backbone behind a lot of modern machine learning models. It's especially used in recent popular large language models like Transformer, BERT, GPT-4, and so on. Like the paper that introduced Transformer was called "Attention is All You Need." And it was talking about how important attention is, roughly at a very high level. In attention, you're given as input matrices that describe tokens or words, and the goal is to find correlations between them in something called an attention matrix, so that you can figure out which of them are important in the context of the sentences you're dealing with. Okay, this is what attention is, but today I don't really want to tell you about like the merits of transformer models or why attention is defined exactly how it is, or why is ChatGPT so popular, or so on. I want to tell you about an algorithms question, which is how quickly can we perform attention? So let me start again and tell you what is the algorithms problem. I'm going to tell you about it today. Okay, so in attention, the algorithms problem, you're given as input 3 matrices. They're usually called the query, key, and value matrices, but I'll call them Q, K, and V, and they're n by d matrices, where today let's think of d as like a lot smaller than n, like log n. So in terms of these, we define this important n by n matrix called the attention matrix. And it's defined like this. You multiply Q times K transpose, so you get a low rank n by n matrix. You divide all the entries by d to rescale it, but then you entry-wise exponentiate all the entries of the matrix. This is sometimes called softmax attention. You're like doing a softmax to the entries. So you get this attention matrix A, and then there's one more important matrix D, which is a diagonal matrix where you multiply A by the all ones vector, so you get like the row sums of A. And then you think about multiplying D inverse times A. So this is like normalizing A so that all its row sums are 1. So you can think of the rows as like a probability distribution. Okay, so these are the ingredients. And then in the attention problem, the goal is to output D inverse times A times the last matrix V, which is again an n by d matrix. So this is the problem I want to tell you about today. And usually it's not necessary to exactly compute this. Usually it's okay to approximate it somehow. So I'll focus today on like infinity norm errors. So like we want an entry-wise approximation to this. We want all the entries to be within epsilon, like 1 over poly n additive error of what they're supposed to be. Okay, so this is the attention question. And then you can ask, how quickly can we do this? Well, the kind of straightforward algorithm where you just work through all the definitions takes about n squared time. Like you first multiply Q times K transpose, which gives you an n by n matrix you can do about n squared time. You entry-wise exponentiate in n squared time. You multiply by all ones vector in n squared time. You multiply by V in about n squared time. If you just straightforwardly do all these things, each step takes about n squared time. Okay, on the other hand, this is a problem where the input and output sizes are a lot smaller than n squared. Like where the input and outputs are just n by d matrices, which are like size n log n. So you could, in principle, hope to do a lot faster than this. But on the other hand, this attention matrix, it's really an n by n matrix. It has n squared entries, and like right in the middle of the definition, we're entry-wise exponentiating it. So in order to hope to do faster than n squared time, we really have to do something that like implicitly makes use of the matrix A and doesn't like actually compute most of the entries of A or something like that. Okay, so in this talk, I want to tell you about algorithms and lower bounds for this problem. And what I'll show you is that basically how quickly, whether or not you can speed this trivial algorithm up and do it faster than n squared time depends on how big the entries of the Q, K, and V input matrices are. Okay, so here's more specifically our results. And throughout a lot of the talk, I'll put this blue box here to remind you what the definition of the question is. Okay, so our main result is that how quickly you can perform this attention computation critically depends on the magnitude of the entries of the input matrices. So let me call that magnitude B. So B is some number, and we're promised that all three of Q, K, and V, their entries have magnitude at most B. Okay, so we have two results. The first is a new algorithm that says if B is less than square root of log n, okay, so there's this threshold square root of log n, and if B is less than that, then there's actually a very fast, nearly linear time algorithm for this problem. You can do way, way faster than n squared time. You can get all the way down to n to the 1 plus little o of 1, almost linear time in the input size. And our second result is a lower bound that if B is bigger than this, if B is even just some big constant times square root of log n, then there's no algorithm that runs in truly subquadratic time, n to the 2 minus delta for any constant delta, assuming the strong exponential time hypothesis from fine-grained complexity. So there's really a very sharp threshold here where if B is less than square root log n, you can solve it as fast as you could hope for. And if B becomes bigger than square root of log n, suddenly you basically can't beat the trivial algorithm for the problem. And yeah, I'll mention, okay, so there's been previous like experimental work showing that techniques that make these matrices have smaller entries can actually lead to faster algorithms, like techniques like quantization, like rounding or hashing, techniques like low degree approximations that I'll talk about more later, have actually led to faster algorithms in practice. So maybe our theoretical result helps to explain this type of thing. Yeah.
I'm just surprised that the entry size matters so much. Can't you just scale it up and down, or is it an aspect ratio? Or...
Yeah, it's like a the entry size. You'll see soon. Yeah, basically when the entry size gets bigger, the relative ratio of entries of the attention matrix gets very large, and this ends up being very important. Yeah. Yes.
I think this is under the assumption that D, the dimension, is order log n.
Yeah, that's right.
Scale D up. How fast is this break?
Yeah, very quick. So often you can, depending on exactly what you want, you can use like dimensionality reduction to kind of assume it's. Sorry.
Repeat the question.
Oh, sorry. The question is how important is this dimension? Is that the dimension is D log n? It ends up being, we'll see, pretty important for, especially for the algorithm. We're really going to use this. Like if the dimension is even like log n to the 1.5, things are really going to break. But often, depending on the details, you can do something like dimensionality reduction to kind of assume your dimension. Not exactly, but it seems to be a situation that comes up pretty often for this problem. Yeah.
And in this lower bound, so if just one entry is huge, is it enough?
You need a lot of the entries to be big. Yeah. Like about half the entries are big. Yeah. And about half the entries are 0, basically. Yeah. Yes.
Is the entry-wise approximation guarantee really important for applications, or like how does it connect kind of with the motivation?
That's a great question. So the short answer is I'm not really the best person to ask that. These papers at least talk quite a bit about how you can, like especially this one on quantization, sort of replaces the coefficients with smaller ones and shows that like the answer you get at the end doesn't seem to change too much. But yeah, it's kind of, there's kind of a trade-off here between you would want bigger entries in order to have a more expressive learning model, but you need smaller entries in order to do solve the problem faster. Okay. So in the rest of the talk, my goal is to show you the proofs of both of these and especially focus on where this square root of log n is going to come from. So hopefully that'll answer your questions about it. So let me tell you about the high level idea of what we do. And this is the high level. I think this is sort of not the high level idea of our algorithms, but the high level idea of how Zhao and I came up with our algorithms. Okay. And it's to take advantage of the similarity between this attention problem and another problem called Gaussian kernel density estimation. So here's again the definition of the attention problem. And there's a really similar problem many of you have probably seen before called batch Gaussian kernel density estimation, which is very, very similar. You think of A as like the kernel matrix instead of the attention matrix. You no longer have this D rescaling diagonal matrix here. And then you just output A times V instead of the rescaling of A times V. Okay, this is, yeah, when you think about what this problem is, you can write it in exactly the same kind of way. It looks very, very similar, right? And Gaussian kernel density estimation is very well studied. I think there are even at least 2 other talks in this workshop that are going to talk about kernel density estimation. So our approach is to show that a lot of the techniques from the fine-grained complexity of kernel density estimation can also be modified to work for this attention problem. So another way you can think about my talk is kind of giving like a survey of techniques in the fine-grained complexity of kernel density estimation, and then modifying them a little bit to work in this situation also. Yeah.
In the Katie problem, you kind of need a minus sign, right? That's kind of where the hardness is coming from. There's like a minus in the exponent.
Yeah, but well, you can negate the matrices to also get a minus sign. Yeah. The matrices, they can have positive and negative entries. Yeah. Okay. So that's our high level. So let me tell you in more detail about the technical ideas, and then the rest of the talk is going to be about going into even more details about these. Okay. So for the lower bound, we're going to use attention computation to solve the approximate closest pair problem. So this is a problem, you're given as input a bunch of points in log n dimensions, and you want to find approximately the closest pair of them. There's a really nice result by Aviad Rubinstein from a few years ago that showed that this problem requires roughly quadratic time, assuming the strong exponential time hypothesis. So we're going to reduce from closest pair to this attention, and since closest pair needs n squared time, attention is also going to need n squared time. And this is an approach that I think the first one to use this approach was this nice paper by Backers, Indyk, and Schmidt from 2017, where they applied it to kernel density estimation, and it's been since used for lots of kernel density estimation problems. There's even a recent work that applied it to attention to get some fine-grained lower bound from attention with in a sort of a different parameter setting. But it's I think a popular approach now, and we're going to apply it here also. And then the algorithm, I'm going to use, I think, my favorite algorithmic technique, which is the polynomial method, which has also been used for KDE before. Like if you're familiar with fast multipole methods, they critically use low-degree polynomial approximations right in the middle of them. But we're specifically going to use like a more recent approach to using polynomial in a slightly different way for this type of problem. And we're going to make use of actually quite recent new upper bounds on polynomials to approximate exponentials, which is going to play a key ingredient in the middle. Okay, that's the plan. I'm going to tell you about these things. And I'll mention that there are other popular techniques from kernel density estimation, like locality sensitive hashing and so on. These have also been previously applied to attention. We're not like the first to notice that attention looks like kernel density estimation. But these types of techniques, usually you like if the dimension is higher than log n, like people are asking about, then hashing is more effective than just polynomial methods. So. Okay, so here's the outline. I'll start by telling you about the lower bound, and then I'll tell you about the algorithm, and then finally I'll tell you about polynomial approximations for exponentials, which is like the technical powerhouse behind the algorithm. Okay. So again, our plan is we're going to reduce from the approximate closest pair problem to the attention problem. So let me remind you, what is the 1 plus epsilon approximate Hamming closest pair problem? So this problem, you're given as input nx vectors and ny vectors. There's 0, 1 vectors of dimension d, like order log n. And you're also given some threshold t. You should think of t as some constant that's between 0 and 1. And the goal is to distinguish between 2 cases. Okay, in case 1, there exists a close pair. There exists an I and j such that the ith x vector and the jth y vector have Hamming distance at most t times the dimension. And case 2 is that they're all 1 plus epsilon far from this. For all the pairs of an x vector and a y vector, their distance is at least 1 plus epsilon times t times t. Just think of epsilon and t are both small constants here. So how quickly can we solve this? Okay, again, this straightforward algorithm is quadratic time. using like standard nearest neighbor search tools, you can, like locality sensitive hashing, you can solve it in subquadratic time, like n to the 2 minus order epsilon. The fastest algorithm runs in this time, n to the 2 minus like cube root of epsilon. So if you're thinking epsilon is like a small number, less than 1, then cube root of epsilon is bigger than epsilon, and then you're subtracting it away in the exponent. So this is a faster algorithm than the LSH one. Okay, this is the fastest known algorithm. And actually, this algorithm uses the polynomial method. So this maybe gives some insight into why the polynomial method should be helpful for attention. We're like reducing closest pair to attention, and the fastest algorithm for closest pair uses polynomial method. So maybe this gives a hint that polynomial method should also be helpful for the attention problem. Okay. And then the key fact about this problem we'll use is this hardness result by Aviad, who showed that assuming the strong exponential time hypothesis, basically for any delta in the exponent, there exists an epsilon so that you can't do 1 plus epsilon approximate Hamming closest pair in time n to the 2 minus delta. So the delta ends up being, you know, something smaller than this, or bigger rather than this epsilon to the 1 that we're subtracting. Okay, you can think of this problem as epsilon gets small enough, really requires pretty much quadratic time. Okay, so let me first do one trick, which is I'm going to convert from closest pair to a different related problem, maximum, like approximate maximum inner product, which is going to be helpful because attention, you know, involves lots of inner products in the attention matrix. Okay, so given as input these nx vectors and ny vectors, so let me define some things. So for a given one of the x vectors, which is a dimension d01 vector, so first I'm going to let xi with a bar on top be the bitwise complement. So the entries that were 1s are 0s, and the entries that were 0s are 1s. And then I'm going to let x prime be the concatenation of x and its complement. Okay, so this is a vector of length 2d now, still of 0s and 1s, but it has some nice properties. First is that now xi prime, it's half its entries are 1s and half its entries are 0s, because you match each entry with its complement entry in the second half. And also now the distance between vectors before, you can write in terms of the inner products of these new vectors. So like you can check that the distance between the prime vectors is twice the distance between the original vectors, because the distance between the complements is the same. And the distance between the prime vectors, you can write it as the number of 1s in x prime plus the number of 1s in y prime minus twice their inner product. This is like counting, we're like counting how many entries have a 1 in one of them and a 0 in the other. So there's like the number of 1s in the first plus the number of 1s in the second, plus we subtract away 2 times the number of entries where they both have a 1. So then that'll count the number of entries where exactly one of them has a 1. And because they're both half 1s and 0s, this is 2d minus twice the inner product. So using this trick, our goal for this problem is equivalently to find an epsilon approximate maximum inner product, given as input a bunch of vectors with half 1s and half 0s. Okay, so now let me convert that into an attention matrix. Here's the attention problem again. And the idea at first is quite simple. We're just going to make our Q and K matrices exactly consist of these inputs to the maximum inner product problem. So we'll concatenate together. We'll make Q transpose be a D by N matrix, which is all the x prime vectors. K transpose will be all the y prime vectors. And we're going to multiply them by B, the magnitude that's going to be important to us. So these are matrices whose entries are either 0s or Bs, or in the case of 2Bs. And they're N by D matrices. Okay. So now, how is the attention matrix defined? Well, its ij entry is exactly this: e to the power of the inner product between the ith column of Q transpose and the jth column of K transpose, which is b squared times the inner product of the xi prime and yj prime divided by d. So in our case, we need to distinguish, to solve maximum inner product, we need to distinguish between two things. The first is that all of them have small inner product. All their inner products are most t times d, which means that in the attention matrix, all the entries are at most x, like e to the power of t times b squared. Just plugging t times d into this. Okay, and I'm going to call that number t tilde. This is like an important threshold for us. So case one, all the entries are at most this number t tilde. And the second case is that there exists an entry where the inner product of the ith and jth vectors are at least 1 plus epsilon times t times d, which means the ijth entry of the attention matrix is at least e to the 1 plus epsilon times t times b squared. And if we pick b to be a big enough constant times square root log n, so that like epsilon times d times t times b squared is like 10 times log n, let's say, then this is like way bigger than t tilde. This is like n to the 10 times t tilde. This is where the square root log n is going to be important for our lower bound. Okay. So this is how we construct our matrices. And now, Rosa, let me just remind you, our goal is to distinguish between the two cases. First case is that all the entries of the attention matrix are between 0 and t tilde. And the second is that A has a way bigger entry that's like n to the 10 times t tilde. So now, if we were doing kernel density estimation instead of attention, we'd basically be done. So if we could compute A times V instead of D inverse times A times V, then we could pick V to be just like the all ones vector, like the all ones vector and then a bunch of zeros for the rest. So when you do A times V, it computes the row sums of the attention matrix. And if one of the entries is, you can just check if any of the entries is bigger than n to the 10 times t tilde. Because if we're in the first case, all the entries are going to be at most n times t tilde. So there's a very big gap between how big the entries would be. However, in our case, for attention, we don't get A times V, we get D inverse times A times V. And exactly the definition of D says that D inverse times A times the all ones vector is always going to give us the all ones vector. So this D inverse scaling sort of exactly messes up this approach. Okay, but we can modify what's going on just a tiny bit so that D inverse doesn't impact what's going on too much, and we can still make this approach succeed. So here's the idea. I'm just gonna increase the dimensions of Q and K by constant factors. I'll make them like this now. So Q and K, here they are, like the top left blue parts are exactly what they were before, but I'm just adding in D more rows and D more columns and N more rows, where I'm putting it in Q like a bunch of ones on the right side, and in K I'm putting zeros in the top part and ones in the bottom part. Okay, so I'm just increasing the dimensions by constant factors like this. What's the point of this? Well, now if you look at what's the ith row of the attention matrix, the first n of the entries are exactly the same as what they were before. Like these ones and zeros don't impact the first n columns of the attention matrix at all. But the second n columns are all the same number, exponential and b squared, because they're just inner products of ones and ones. Okay, so and if b is a big enough constant times root log n, then this is some number that's n to the power of some big constant. So in particular, all the entries of D inverse now are nearly identical to each other. They're all the entries of D are like within a factor of 2 of each other, because you have n entries that are as big as possible, and then n other entries that are like between 0 and that value. All the row sums of this new attention matrix are the same within a factor of 2. All the entries of D inverse are about the same as within a factor of 2. But if we pick V to be the vector that's ones for the first half and zeros for the second half, then A times V is like the same as before. So now D is not hurting us too much. It's just scaling things by a factor of 2. But still, like before, we're looking for an entry that's like n to the 9 times bigger than the other entries. So this we'll still be able to detect the close pair letters. Okay, this is the trick to make it work for attention. Okay, so that's the lower bound and where the square root log n comes from here. Let me tell you about the algorithm now. So in the algorithm, okay, we want to solve this problem in nearly linear time, and here's our plan. What we're going to do, we want to implicitly make use of this attention matrix A without really explicitly computing all its entries. So our goal is going to be to compute a low rank approximation of A. We're going to try to compute matrices L and R that are n by m for some m that's way smaller than n, such that L times R transpose is approximately equal to A. I'll call it A tilde for L times R transpose. Okay, why is, if we do this, let me show you why we can do the whole attention quite quickly. Well, first of all, we can approximate D. So D, it's supposed to be, you take A times the all ones vector and then turn that into a diagonal matrix. We could instead compute A tilde times an all ones vector and turn that into a diagonal matrix. And you can do that quickly by first multiplying R transpose times all one vector in n times m time, and then multiplying L times that in n times m time. So you can compute an approximation to D that I'll call D tilde quickly. And then you can compute the output. Instead of outputting D inverse times A times V, we'll output D inverse tilde times A tilde times V. And again, by breaking up A tilde into L times R and doing first R transpose times V, then L times that, then D inverse tilde times that, you can also do this in n times m time. So if we have this decomposition, the whole thing takes n times m time. And I'll spare you some calculations, but it suffices to have A tilde be an approximation of A, where each entry has to be like at most epsilon over 2 away from what it's supposed to be. And then you kind of get two error propagations, one from A tilde, one from D tilde, and the whole thing will still be within epsilon of what you're trying to output at the end. And we need m to be n to the little o of 1 so that this algorithm runs in time n to the 1 plus little o of 1. So this is the plan. How do we find these matrices L and R now? Well, the key tool is going to be polynomial approximations of the exponential function. So here's what I mean by that. So in these approximation, there's two parameters. There's b, the like interval you want to approximate it over, and epsilon, how much error you're willing to tolerate. And we know that for any b and epsilon, there's a polynomial that for any x between like minus b squared and b squared, which it will be the range that we care about, approximate it with an additive epsilon, and it has degree this, the maximum of two terms. Okay, one of those a b times square root log 1 over epsilon, and others more like log 1 over epsilon over some log factors. And actually, interestingly, the details of what these log factors are was only nailed down recently in this work last year, and it's going to turn out to be really, really important for our algorithm. So yeah, we'll see in a couple of slides, but figuring out what these logs were will turn out to be important for making our algorithm be fast enough. And this is tight. We have matching upper and lower bounds that this is the degree you can get. Okay, so how are we going to use this? So the idea, this is often called the polynomial method in algorithm design. Oh, yes.
Does the size of the coefficients matter to you?
It could matter in principle. Here, the coefficients they're all polylog in the relevant parameters, so it doesn't impact it. In principle, it could be important, but it turns out they're small here. Yeah, great question. Okay. Okay, right. So our goal is to compute these matrices L and R so that LR transpose approximates A. Okay, so here's how we're going to do it. So let me introduce a little bit of notation. So let me write Q sub I for the ith row of Q and K sub J for the jth row of K. So these are vectors of length D, like order log n. And the ijth entry of the attention matrix is supposed to be e to the inner product between Qi and Kj divided by D. Okay, so what I'm going to do is let P be the polynomial I just mentioned, the polynomial of degree G that epsilon approximates e to the x on this interval between minus b squared and b squared. And I'm gonna, my approximation to the attention matrix is just going to be defined exactly the same way, but instead of x, I'm gonna write P. So I'm gonna use my polynomial in the definition of the matrix. So you can see, like immediately, this A tilde is a good entry-wise approximation of A. It follows directly from the fact that P is a good approximation of e to the x. But what we need to do now is compute these matrices L and R so that L times R transpose is equal to this A tilde matrix. Okay, and here's the idea. So P evaluated at the inner product of Qi and Kj, we can expand it out like this, what the inner product means. We're going to think about this. It's a polynomial in 2D variables, like the D entries of Qi and the D entries of Kj. Its degree is G, the degree we just talked about, because we're plugging a linear polynomial into a degree G polynomial. And the m, the dimension we're going to get, is going to end up being the number of monomials when you expand this thing out, which you can do some counting argument and see it's 2D plus G choose G monomials that this will have when you expand it out. Okay, so remember our goal is we want to make these L and R matrices. So for each Qi, we want to make a vector Li of length m. And for each Kj, we want to make a vector Rj of length m, so that the inner product of Li and Rj should equal to the polynomial evaluated at the inner product of Qi and Kj. And we'll do this by just expanding out this polynomial up here in terms of its monomials. So here's an example where I've expanded a polynomial in terms of some monomials. And the trick is that we can write this as just the inner product of two vectors, where in the first vector, we're going to put like the q part of each monomial. And in the second vector, we're going to put the k part of each monomial. So when you entry-wise multiply like the first entry of the first matrix and the first entry of the first vector and the first entry of the second vector, you exactly get the first monomial, and so on. And when you take the inner product between these two vectors, it's exactly evaluating the polynomial. So these two vectors evaluate the polynomial, but importantly, the first one depends only on Qi, and the second vector depends only on Kj. So these are exactly the Li and Rj vectors that we needed. Each entry can be computed very quickly. You just multiply together some entries of the Q and the K vectors, and the length is the number of monomials in the polynomial, which is this binomial coefficient. That's how we make these matrices, L and R. Okay, so then what's the running time we get at the end? Well, so what I just showed you is roughly you can solve the problem in time n times m, where m is this binomial coefficient. So let me remind you what all these things are. G is the degree of our polynomial approximating e to the x, which is this weird expression. And what are the other things? D is like order log n. Epsilon I'm going to think of as 1 over poly n. Okay? So now we can plug in some things into these expressions and see what we get. Well, first of all, if b is small o of square root log n, then the degree G is also going to be small o of square root log n. Okay, the first term is like small o of square root log n times square root log n. The second one is log n divided by log of log n over small o of log n. Oh, I think there's supposed to be a 2 here. But okay, anyway, but both of the terms are small o of log n. So the degree G is small o of log n. So m is like log n choose small o of log n, which is n to the little o of 1. And you get a final running time that's indeed n to the 1 plus little o of 1 time. And by contrast, you can see once b is just a bit bigger, like some big enough constant times square root of log n, then this m is, like g is now some constant times log n, and now m is like some constant choose times log n, choose another constant times log n. It's really polynomial in n. So this algorithmic approach no longer works when b just gets to some constant times square root log n. And furthermore, by the lower bound we talked about before, actually assuming Ceph, there's no algorithm that can beat n to the 2 minus little o of 1 in this case. Well, not only can this polynomial not beat it, but assuming Ceph, no algorithm could beat it. Yeah.
So your polynomial improvement was this log factor in the second term in the denominator?
Yeah, that's right. I think there's supposed to be a 2 here, so that this makes the difference between this being super constant or a constant.
So just to make sure I'm understanding, if, like you said, if that term wasn't there, then G would have degree, I guess, log n, and then this whole method would not go through it then.
Yeah, exactly. Yes, this like log factor ends up being important because it like shows up in the exponent in what m is. Yeah.
So epsilon 1 over polynomial, is that important or?
Okay. So my understanding is when you like apply this attention in these transformer models, there's like kind of a polynomial number of units you're applying it to. So you need like if you want to accumulate all the errors.
No, not for for your result. Yeah.
Yeah, exactly. If the error is smaller, then like both the degrees get smaller. I think there's certainly the degree gets smaller and you get a faster algorithm. I think there's probably more straightforward things you could do if you want smaller than polynomial errors. So it's like something like random sampling of coordinates. Yeah. Okay. So I think I have like 10 minutes left let me talk a little bit about where this degree actually comes from, because it's kind of the powerhouse behind the whole algorithm, and I just claimed it without telling you anything about it. Great, so I told you, there's a polynomial of degree this for approximating e to the x. Where does it come from? And the main idea is to make use of a nice family of polynomials called Chebyshev polynomials. So Chebyshev polynomials, this is a family of polynomials, like for any degree d, there's a dth Chebyshev polynomial. They have lots of equivalent definitions. One nice one is this trigonometric definition that when you plug in cosine of theta, it gives cosine of d times theta times some scaling factor. But if it's not, maybe it's not clear to you, depending on how much like high school trig you remember that this is a polynomial, you can equivalently define in this nice recursive way, where it's very clear it's a polynomial, and you can check by induction that these two definitions are really equivalent to each other. So what do these polynomials look like? Well, here's an example of the 10th Chebyshev polynomial. So like between -1 and 1, they're wiggling up and down like a kind of like a cosine because of the trig definition, and then outside of that interval they blow up like a polynomial ought to. So the one really nice thing about Chebyshev polynomials that makes them useful here is they have really nice extremal properties. So for example, it's known that among all the polynomials of degree d, such that in this interval between -1 and 1, they're always bounded by, the scaling factor 2 to the 1 minus d. The Chebyshev polynomial is the one that maximizes the value of the polynomial for every point that's outside the interval from -1 to 1. So like here you can see the polynomials, but I rescaled it by the 2 to the d minus 1 factor. So between -1 and 1, it's bounded between -1 and 1 because of the trig property. But then anywhere to the right or to the left of this box, the Chebyshev polynomial is the one that gets the biggest possible value. Okay, so why is this relevant to approximating exponentials? Well, so let me give an example of how we can use this extremal property to actually show a lower bound on the degree to approximate e to the minus x. Okay, so here's like a picture of e to the minus x, and if we had a polynomial that was going to approximate this, it would at least have to have two properties. The first is that over here in the tail, it can't be more than delta away from e to the minus x. So over here to the right, it has to stay within this red box. And then all the way to the left, it has to get close to 1, like e to the 0. So to the right, it has to stay bounded within this box. And to the left, it has to get quite large, close to 1. And so you can check, first of all, what's the minimum degree of a Chebyshev polynomial that achieves just these two properties. You can do some work and see that it's b times square root of log 1 over delta. And so because the Chebyshev polynomial is the minimum degree polynomial that satisfies these two properties, that gives a lower bound right away that the degree to approximate e to the minus x has to also be at least b times square root log 1 over delta. So this is like you can pretty quickly use Chebyshev polynomials to get lower bounds on the degree required. It turns out Chebyshev polynomials for this kind of reason are also useful for the upper bounds. So how is it that we go about approximating e to the minus x with polynomials? Maybe the first idea is you would just write out a Taylor series for e to the minus x and truncate it. And you can do this, and it gives a decent degree d approximation. But an idea that turns out to work better is to truncate the Chebyshev series instead. So you do a change of basis. Instead of writing it out in terms of monomials, as a series in terms of monomials, you write it out as a series in terms of Chebyshev polynomials. And you truncate that polynomial instead, and it turns out to work better much more quickly. So here's an example of just approximating it with degree 4. Like here's the Taylor expansion looks like this. And the Chebyshev expansion looks like this. It's like wiggling up and down like a Chebyshev polynomial does. And you can see even in this small case, like the Chebyshev polynomial already gets like 1/5 the error of the Taylor expansion. So even very quickly, these Chebyshev polynomials are important for approximating exponentials. And you can prove more generally, like if we had any function at all, we wrote this. It's sort of a well-known fact in polynomial approximation theory that Chebyshev series truncations work very well for approximating functions. So if you had any function at all that you write as a series in terms of Chebyshev polynomials, and you let P be its best possible approximation, not necessarily coming from Chebyshev polynomials, then you can both upper and lower bound how good the approximation has to be in terms of the coefficients in the Chebyshev series. So the upper bound just comes from if you did that Chebyshev truncation, then because each of these rescaled Chebyshev polynomials is always at most 1, you just do a triangle inequality and you get this upper bound. The lower bound, you have to do a little bit of work because like the Chebyshev polynomials can interfere with each other a little bit. But if you do like an appropriate L2 analysis, you can show a lower bound that looks like this also. And in particular, if these coefficients in the Chebyshev series decay quickly enough, then the upper bound and lower bound here are very, very close to each other. It roughly says that like the d+1 coefficient is really the one that matters. And you can do a bit of work and show that for exponentials they do decay quickly, and you can even improve this bound for in the special case of exponentials. And this is the idea behind how to get the tight degree for the expansion. Okay, that's it. Thanks.
Dr. Richard, any questions?
Hey, do you think your hardness result continue to hold if you take epsilon to be some small constant? I think currently the hardness result hold for epsilon to be like 1 over poly n, right? But do you think it's like continue to hold when epsilon is some constant?
Oh, epsilon's a constant.
Like
probably not. I mean, I think like the polynomial method would actually give a fast. Well, maybe actually it's not so clear. I think the lower bound. Oh, it probably needs something like 1 over n. Yeah, actually, I suspect it really needs epsilon to at least be 1 over n to some particular constant. I think for lower error than this, there probably are faster algorithms, not using polynomial method, but using like random sampling and hashing and things like this.
But I think the problem is like you take a exponential, you take e to that every entry. So it's kind of...
Yeah, but there's like so like there are going to be other talks in this workshop about using like hashing methods for kernel density estimation that work better for small, like they usually have polynomial dependence on epsilon, but then worse dependence on d. But I think if you use those kinds of approaches, like a totally different algorithmic approach, it actually works well when epsilon's like a constant. Yeah.
Hi, Josh. Nice talk. So I have a question on both the algorithm side and the lower bound. So for the algorithm, I mean, like right now, it's to me at least, it seems like you need every entry to be like less than square root of log n or something. But let's say most of the entries are guaranteed to be like less than square root of log n, but some of the entries could be bigger. Can you modify your algorithm to still work there, or it's not known?
Yeah. Depending on the details, most likely, like maybe you could just correct the specific entries where the polynomial approximation, you know, it's going to be wrong, or you could, there's like in multiple methods, you kind of partition up space into a bunch of cubes, and then you like say the polynomial works well between pairs of cubes, and assume there can't be too many cubes that points are in and things like this. There are tricks for dealing depending on exactly what the details are.
Sounds good. So on the lower bound side also, it's like, so you have like half of the entries, like at least like bigger than like square root of log n or something. So so in general, like let's say if only like little of n square entries are like bigger than square root of log n or something, what do you expect? Like, do you think there'll be a better algorithm, or you think there could be a lower bound? Like,
probably. I mean, you could. I see. Like, yeah. So maybe then you like partition up the matrix into the sparse part and the small entries part, and can separately deal with both of them. I guess there's algorithms you could do. I have to think about it.
sounds good. Okay, thank you.
Final question? No, thanks, Josh, once again. There's now a 30-minute break into the last talk of the morning.